A projectile is an object upon which the only force is gravity. Gravity acts to influence the vertical motion of the projectile, thus causing a vertical acceleration. The horizontal motion of the projectile is the result of the tendency of any object in motion to remain in motion at a constant velocity. Due to the absence of horizontal forces, a projectile remains in motion with a constant horizontal velocity. Horizontal forces are not required to keep a projectile moving horizontally. The only force acting upon a projectile is gravity. Now here's a video physics which displayed my plotted points as well as the graphs such as the x component, the y component, and the x velocity and the y velocity. Now although those graphs were fine, I decided to graph them on a graphical analysis tool, which I will constantly be referring to when I make my comparisons between the actual equations which I calculated and the ones which we can see on the graphical analysis tool, which just show us the difference in numbers. And I'll constantly be referring to these throughout the whole video. Okay guys, so what you're seeing is a right angled triangle which I drew up to calculate my initials. So as you can see, I've obviously got my initial velocity on the x and the y, so you got 3.72 on the x and 5.82 on the y, and I use this to calculate my initial velocity, which I calculated to be obviously through the square root of x dot squared plus y dot squared, which is just the formula, and I got 6.9 meters per second. And also I used the x dot and the y dot to calculate my angle through the tan formula, and I got 57 degrees and 25 minutes. I particularly used this because it was very difficult to use a protractor on the camera and it was very inaccurate, so I just resorted to calculating it through the use of my knowledge of projectile motion. Also, you're seeing the initial conditions which I just stated to make the end calculations much easier. Okay, so my next step in the calculation process was I calculated the horizontal and the vertical. So I did this, let's start with the horizontal. So I started off with the acceleration as 0, of course, and integrated it to get c. We found c to be 3.72 through the initial conditions, which I stated earlier. We then integrated that over time, and we received 3.72t plus c to get our x, and our final x was obviously 3.72t because initially it started at origin, and so c was 0. So next with the vertical, I started off with my acceleration. As spoken of before, we use gravity, which is negative 9.8 meters per second squared, of course. So we then integrated that and we received negative 9.8t plus c. Earlier with our initial conditions, as I stated, we have 5.82 when t equals 0, and you can refer back to this. So we received c equals 5.82 and then reintegrated that to get 5.82 t minus 9.82 t squared over 2 plus c as our y. And from there we use t equals 0, and at t equals 0 I estimated from when I released the ball from my hand to be approximately 1.7, as I am 1.93 meters and I released it somewhere near 3/4 way down my body, so I calculated 1.7. We then obviously end up with the end result as 5.82t minus 4.9t squared plus 1.7 equals y. Now my time of flight calculated, I made y equals 0 and I solved the quadratic equation using the quadratic formula. My end result was t equals 1.39 seconds, and I had two values, one was a positive and one was a negative, and obviously we disregard the negative because time must be greater than or equal to 0. So my calculated time of 1.39 seconds compares to the graphical data, which says 1.63 seconds, and in fact that's a very small difference, and it just shows how accurate we were in calculating our vertical and horizontals. Okay, so next I calculated the range. I just subbed in the numbers. So I subbed in obviously my initial of 3.72, and I times it by the time of flight, and this gave me the number of 5.1708 meters. And once again, my calculations did prevail, and it was very, very close to the range on the given on the graph, which was 5.23, which is less than 0.1 of a discrepancy. Next, the maximum height was calculated by first making the y velocity equal 0, which allowed us to calculate t as somewhere near 0.5938, etc. And at this t, we then subbed it in to the y, and we got a value close to 3. And this is quite accurate, as the actual maximum height calculated on my graph is 2.7, so it's somewhere near a 0.3 or 0.2 discrepancy there. Now, although it wasn't required, I just quickly made a Cartesian equation by making t the subject, subbing it in as we normally do, so back into the y, and I received the value of y equals negative 0.35x squared plus 1.56x and plus 1.7. You'll see this on my Desmos graph. So what we can see from this is it's actually quite accurate to the calculations. So we see that obviously it starts in the initial position of 1.7, which is where the ball was released from my hand. We can see the range, which is 5.1708, and obviously the maximum height, which was somewhere near 3.4, and that's quite accurate to what I had calculated. Just to end this video off, obviously there were quite few discrepancies between the calculations, the data that I had, and the graphical analysis tool that I used at the beginning, and I had made comparisons which you can constantly refer back to. But there were discrepancies, and we do need to account for them. My main thinking behind these discrepancies is obviously air resistance. Although the 3-unit course does not take us through the effects of air resistance, it is definitely present. And the day we were actually filming this, it was quite windy, and so air resistance definitely accounted for these discrepancies, as well as things such as a moving camera, which could have slightly affected the graphical analysis tool, among calculation errors and in significant figures that we can account for too. Just to end it off, this was quite a successful investigation, as we were able to calculate pretty much everything, from the initial conditions to the Cartesian equation, which we compared at the end, and I feel that it was quite successful in demonstrating how we can use projectile motion and our skills in calculating projectile motion in the real world with data.